In this video, we are going to study some of the convergence properties of the Fourier series. Now, we know that for any arbitrary periodic signal x of t, if x of t satisfies certain conditions such as absolute integrability over a period, we have a Fourier series representation for that signal. So let us consider x of t is an arbitrary periodic signal with fundamental period capital T0. So x of t has the Fourier series representation given as x of t is equal to k from minus infinity to plus infinity ak e to j k omega 0 t, where omega 0 is related to the fundamental period by means of this expression 2 pi over t0 is equal to omega 0. Now, in signal processing literature, sometimes the Fourier series is called as the Fourier sum, but this is a somewhat incorrect term because the Fourier series is a series containing infinitely many terms, and therefore we need to discuss about the convergence of such an expression. Okay? Now, in order to study the convergence properties of the Fourier series, we consider the so-called truncated Fourier series. Consider the truncated Fourier series. In fact, we can call it the partial sum because now we have a sum containing finitely many terms. So we are going to denote this by Sn of t. Sn of t is defined as k running from minus capital N up to capital N ak e to jk omega 0 t. Now this is in fact a sum. It's a summation operation because we have only a finite number of terms and therefore summation is valid. But in the case of a Fourier series, we don't have a sum anymore. We have a series, and therefore we have the issue of convergence we have to deal with. Now, how can we claim that when n tends to infinity, somehow this Sn of t, the truncated Fourier series, must converge to x of t? So, okay. Now we have to discuss the convergence of the truncated Fourier series Sn of t to x of t as n tends to infinity. Okay? Now let us look at Sn of t. It is equal to k from minus n to plus n, ak e to jk omega 0 t. Now we know how we calculate AKs. Therefore, we can substitute that expression in this finite sum, k from minus n to n, 1 over t0. Now, AK is equal to 1 over t0. And from an arbitrary t0 up to t0 plus capital T0, x of t e to minus jk omega 0 t integrated with respect to t. Okay, this is ak multiplied by e to jk omega 0 t. Now, in order not to get confused with the variables, okay, inside the integration, we can choose our variable as t prime. So t prime, t prime, t prime. Because we are now going to combine the terms containing t and t prime. Okay, so this expression within the brackets is just ak, the kth Fourier coefficient. Okay, then we can interchange summation and integration operations. Okay, we have this expression is equal to from 0 to, not from 0, from t0 to t0 plus capital T0 x of t prime okay, k from minus n to plus n, 1 over t0 e to jk omega 0 t minus t prime. Okay, we have this expression integrated with respect to t prime. Okay, we have just interchanged summation and integration operations. Now, within this bracket, this expression is called the Dirichlet kernel. And we call this the Dirichlet kernel denoted by the symbol d sub n t minus t prime. Okay. Now, we have obtained an interesting result. In fact, if we look at the expression, this is the expression of the partial sum or truncated Fourier series. It is an integral expression of x of t prime multiplied by the Dirichlet kernel dn d sub capital N t evaluated at t minus t prime integrated with respect to t prime. Okay, so what is the behavior of the Dirichlet kernel for larger values of n? Let us now look at this problem. Now, for larger values of n, the partial sum Sn of t is required to converge to x of t. Okay, so on the left-hand side, we will have a convergence to x of t. So the right-hand side must also be equal to x of t. Therefore, the term in the brackets, the Dirichlet kernel, must act like an impulse. Because the action of the impulse, which is defined in terms of the integral, is just the impulse sampling the signal at here the integration is with respect to t prime. Therefore, the impulse will act at t, so the value of the signal at t will be sampled. Okay, now, but let us try to see this formally. Okay, now the Dirichlet kernel dn evaluated at t. Let us look at this expression, because in the integral expression we have the shifted version of dn of t. We have dn of t minus t prime. So it's a shift by t prime. So let us look at the Dirichlet kernel evaluated at t. So it is k running from minus capital N to capital N 1 over t0 e to j k omega 0 t. Okay, now in order to deal with this sum, we follow certain steps. First of all, now this is a sum starting from minus n and running up to n. So let us convert this to a sum starting from 0. So let us take the term e to minus jk e to minus j n omega 0 t as the common term and take it outside the sum. So the sum becomes now a sum from k from 0 to 2n e to j k omega 0 t. Okay. Okay. Now we just write down the expression of this sum. So this is 1 over t0 e to minus j n omega 0 t. Okay, this is the sum of e to j omega 0 t raised to the power k from 0 to 2n. So we know how to find the sum of such an expression. This is equal to 1 minus e to j 2n plus 1 omega 0 t divided by 1 minus e to j omega 0 t. Okay. Now, so we first try to do the following. Now, let us try to reduce this expression to by using the tricks we have previously used in many applications. Let us try to simplify this expression a little bit. Okay, so we write this as 1 over T0 e to minus j n omega 0 t. Okay, now let us take the term e to minus j n plus 1/2 omega 0 t as the common term and write down the terms in the x. Okay. Okay, let us do it in the following way. From the numerator, we take this as the common term, and from the denominator, we take the term e to minus j omega 0 t0 over 2 as the common term. And then we have e to okay, let us not take e to minus but plus. Okay, plus e to j times m plus 1/2 omega 0 t for the numerator term, and the term e to j omega 0 t0 over 2. Not t0, of course, this is t. Sorry. T over 2 as the common term. So we have e to minus j n plus 1/2 omega 0 t minus e to j n plus 1/2 omega 0 t. Okay, divided by e to minus j omega 0 t over 2 minus e to j omega 0 t over 2. Okay, this is a trick used in many other applications as well. In the analysis of the Fourier series, this is a very common technique used. So we take these terms as the common terms outside and write down the expressions here in this way. But we recognize these terms in the numerator and in the denominator as the sine signal. So this can be written as 1 over t0 e to minus j n omega 0 t, and we have e to j m plus 1 half omega 0 t divided by e to j omega 0 t over 2, and we have here the numerator is minus 2j sine n plus 1 half omega 0 t. And the denominator is minus 2j sine omega 0 t over 2. Okay. So minus 2j's will cancel out. Now if we look at this expression here, we have e to minus jn omega 0 t, and here we have e to plus jn omega 0 t, so those will cancel out or multiply, their product will be 1. And we have e to j 1 over 2 omega 0 t, and we have a term in the denominator which is equal to that. So this is equal to 1. This term here is equal to 1. So the Dirichlet kernel turns out to be equal to 1 over t0 sine m plus 1 half omega 0 t divided by sine omega 0 t over 2. Okay, so this is the Dirichlet kernel. Now the Dirichlet kernel is periodic with a fundamental period equal to 2 pi over omega 0, which is our original fundamental period defined for the original periodic signal x of t. Therefore, now if we plot the graph of the Dirichlet kernel over a period, for example, let us look at the Dirichlet kernel in the interval from minus t0 over 2 to t0 over 2. It will have a graph in the following form. It will have a peak at t equal to 0, then we will have the side lobes oscillating. Of course, we will have a symmetric. I couldn't draw this properly. We will have a symmetric. We will have even symmetry. Okay, so for a particular value of capital N, we will have a main lobe peaking at t equal to 0, and we have the side lobes. Now, as n tends to infinity, the side lobes will gradually decrease in magnitude, and the main lobe will tend to an impulse. Okay? So, okay, we can continue here. Now, as n tends to infinity, dn of t tends to the, remember, dn of t is periodic with period t0, tends to the impulse train. Which is the expression m from minus infinity to plus infinity, delta of t minus m t0. Now here we have drawn the graph of the Dirichlet kernel over a period extending from minus t0 over 2 to t0 over 2. And here we see that we obtain the impulse delta of t within this period because the main lobe will tend to an impulse because of the gradual decrease of the side lobes in magnitude. Okay? In fact, we remember that this impulse train has the Fourier series representation given by k from minus infinity to plus infinity 1 over t0 e to jk omega 0 t. So the Fourier coefficients are 1 over t0. Now, obviously, when you compare this to the Dirichlet kernel, this is the Dirichlet kernel written when n tends to infinity. So as n tends to infinity, the Dirichlet kernel tends to the impulse train. So this explains why we have the expression of x of t written as the convolution of x of t with the Dirichlet kernel when n tends to infinity, because when n tends to infinity, the Dirichlet kernel tends to the impulse train. And sampling by an impulse means you sample the value of the function at that particular value. So this illustrates that the right-hand side and the left-hand side are equal. Okay, so this video was about the convergence of the Fourier series. In fact, this is not a very formal discussion. Our discussion in this example is not a very formal discussion, but we just we have calculated the Dirichlet kernel and we have seen the graph of the Dirichlet kernel, and in the limit as n tends to infinity, the Dirichlet kernel tends to the impulse train, etc. But in terms of rigorous mathematics, still there are some important details to be handled related to the behavior of the original function, original signal x of t. Okay, so thanks for watching.